Hi everyone, and welcome to CMY301, Performing Chaos Engineering in a Serverless World. My name is Gunnar Grosch, and I'm really happy to see all of you here today. So, this is the abstract of this talk, and of course, together with the title, having both serverless and chaos engineering in the title, this is hopefully what brought you here today. So, the principles of chaos engineering have been battle-tested for years using traditional infrastructure and containerized microservices. But how do they work with serverless functions and managed services? So this is the agenda and what we'll try to cover today. We'll cover what chaos engineering is. We'll look at the motivations behind doing chaos engineering. We'll look at how to perform chaos experiments, the challenges that are with serverless, and we'll also look at some common weaknesses that we can test for in our applications. And of course, we'll try to finish it off by doing some chaos demos as well. So, who am I, Gunnar Grosch? Well, I am an evangelist at a Swedish company called Opsio, where we help companies build and operate reliable applications in AWS. And I started out in this industry about 20 years ago, straight out of high school, building websites. And it's quite funny that 20 years later, we're still doing static websites and using GIFs on the internet once again. Since then, I've been in both operations and management. And nowadays, as an evangelist, I guess I do a bit of everything in those areas today. So one of my passions is building communities. So I'm deeply involved in the AWS user groups in the Nordics. Also run some serverless meetups in the Nordics. And I'm co-organizer of both Serverless Days Stockholm and the upcoming AWS Community Day in Stockholm. But my true passion is serverless and chaos engineering. So my focus with serverless applications is building resilient and robust applications. So having reliability is my focus. I get the question every now and then why I get started with chaos engineering. And my usual answer there is that I'm divorced and I have 3 kids, so I know all about chaos. Well, truth be told, it's actually more a matter of having seen incidents, failures, outages for many years, where the application architecture and the application code has been best practice. But we still have outages and we still have incidents all the time. So that's how I started looking at chaos engineering. So let's get to it. What is chaos engineering? Well, chaos engineering is not about breaking things. You often hear the phrase breaking things on purpose. And that is great marketing lingo. And it helps draw attention to the practice of chaos engineering. So to be clear, it's nothing wrong with using that phrase, talking about breaking things on purpose, as long as we all agree on that breaking things isn't the real purpose. Casey Rosenthal, he was previously at Netflix and one of the creators of chaos engineering. He famously said that, "I'm pretty sure I won't have a job very long if I break things on purpose all day." And I think that's true. So sure, we do break things when we run chaos engineering experiments, but the breaking part isn't the purpose. Learning is the purpose. Chaos engineering is not resilience engineering. Resilience engineering is something different. Nora Jones, you might remember her from a reInvent keynote from 2017 when she talked about chaos engineering. She wrote a tweet a while back where she wrote that resilience engineering is not chaos engineering. And it's an important distinction to separate these two. One is chaos engineering, the other is resilience engineering. Resilience engineering is an old field, about 20 years old, and it is in critical domains like aviation, power supply, medicine, and so on. But in recent years, the software engineering and operations has become more involved in resilience engineering community as well. Chaos engineering is not only for production. We often hear that chaos engineering should be used in production. And hearing this and saying this can be an obstacle for anyone trying to introduce chaos engineering in their organization. We want to do it as close as possible to production, but you can do experiments in your test environment, in your staging environment, in your playground environment, whatever you call it. But the more production-like, the better, of course. So when working with chaos engineering in other environments than production, think about replaying traffic. Think about using it together with load testing. Whatever you can do to try to make it as production-like as possible. There are a bunch of major companies today doing chaos engineering, and they are nowhere near doing it in production. But they are still very successful with their chaos engineering. Chaos engineering is not only for big streaming companies. There are reasons why Netflix is used as a reference over and over again. Well, they started it. It was at Netflix that chaos engineering was started. So they are also a company with big brand recognition. So it's easy to use them as an example over and over again. But you don't have to be Netflix to do chaos engineering. You don't even have to be like Netflix. And data shows that more and more companies are looking for and hiring chaos engineers, SREs, with the responsibility to do chaos experiments. So the practice of chaos engineering is gaining traction all the time. And chaos engineering is now used by companies ranging from e-commerce to fintech and banking, as well as smaller startups that are aiming to do reliable applications. You can't really have a chaos engineering talk without showing this slide. The Principles of Chaos was a website that was launched together with the first book on chaos engineering. And it says that chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. So reading this shows that it's actually less about doing things that are chaotic and more about experimenting. So the chaos part of chaos engineering is more about our systems and what is inherent in our systems. So there is chaos in every system. So let's break that down a bit. Chaos engineering is about performing controlled experiments to inject failure. So we do experiments, and that makes it sound quite scientific. And to be honest, it is. We create controlled experiments, and we measure the results of those experiments. So some compare it to a vaccine in that we inject failure into a system to make it stronger. Chaos engineering is about finding the weaknesses in a system and fixing them before they break. So no matter how much we focus on making our systems resilient to failure, there are always unknown factors that come into play. We have traffic patterns, we have third-party dependencies, we have network issues, we have code deploys, we have config changes. And by doing our experiments and measuring those results, we can draw out these weak points in our systems. And finding and fixing those, well, that can help us avoid this big outage that never happens at the right time. So most of us likes to sleep at night. And not having that incident, quite good for us. Chaos engineering is also about building confidence in your system and in your organization. By finding these weaknesses and doing controlled experiments, we can build confidence in our system and how the system works. We also build confidence in the organization. It means that the people, they are key in building a resilient system. And by building confidence in our organization, we gain trust in the organization as well. So perform experiments, and you will learn new things about your system. So now we've looked at what chaos engineering is, and I haven't seen all that many people leave the room, even though it's less chaotic now than perhaps when you got there. So it is controlled. So let's look at what the motivations behind doing chaos engineering is. Nines don't matter if users aren't happy. It's a famous quote by Charity Majors of Honeycomb. And we can have dashboards showing our SLAs, our SLOs, our SLIs, but it doesn't really matter if it's green or red, as long as our users aren't happy. So everyone who builds or runs a system has customers, be it may that they are internal customers or external customers. And are your customers getting the experience that they should, or are your customers unhappy? We often say that nothing is free on the internet. So no matter if you run an e-commerce site, an ad-driven blog, or a SaaS solution, downtime or issues in that solution will probably cost you money, be it in decreased sales or just by users not staying on your platform. What happens when there is an incident? Are you confident that your monitoring, your alerting, will actually notice the incident? Will the on-call actually get that page to wake him up so he can start engaging with the incident? We set it up, and we hope that it works. And you probably have runbooks or playbooks that tells you how to act when an incident or an outage occurs. But is the organization actually ready to do the work? Are they comfortable with running the playbook? Hopefully, in your company, you do fire drills, so you know how to act when there is a fire in your building. But do you do fire drills for incidents? Every time there is an incident, we have a huge opportunity to learn about the conditions that exist for the incidents to take place. So we learn from incidents when we have them, but what about learning from controlled incidents, incidents that we create with the help of our experiments? As Ryan Kitchens at Netflix core team says, you are going to have incidents. You just can't choose not to. And having these incidents is perhaps what makes us successful. We all know Werner Vogels, and I think we all know this quote: everything fails all the time. And Werner should know. Many of you here probably remember the big S3 outage in 2017 and how that affected the entire internet. But failures and outages happen all the time. Google had a configuration change in June, which led to Gmail, Drive, most of their apps having major issues. But it also affected third parties relying on their services. A routing issue with Verizon in June led to a big chunk of the internet not working. Cloudflare did software deploy in July, I think, which led to CPU spikes for them, which affected their entire platform and most of their users. Even Netflix had an outage just about a week ago. So everything fails all the time. And that leads us to perhaps the greatest motivation behind chaos engineering. Don't ask what happens if a system fails, but ask what happens when it fails. Remember this, a resilient system isn't one that doesn't fail. It is a system that maintains an acceptable level of service in the face of failure. What happens when the system fails? That's something that chaos engineering helps us find. So now, having set what chaos engineering is and why we want to do it, let's look at how to run chaos experiments. We'll do that by following some simple steps. Before we create our actual experiment, we need to set what we call the steady state. And steady state, without knowing this, we can't really see what happens when we're running our experiment. And the steady state is basically the normal behavior of our system over time. It's highs and lows, it's ups and downs. And to help find this, we use traditional system metrics, CPU, memory, number of hosts, whatever our system metrics are. But we also use business metrics. And watching CPU graphs probably tells us something about our system, but more useful is usually business metrics. And business metrics might be number of active users, it might be number of purchases, clicks, or stream starts per second, as a famous streaming company uses. It's also important to remember that steady state isn't continuous. It changes over time. So a week in June or July is probably different from weeks leading up to Christmas. So now we've set our steady state. The next step is to form what's called an hypothesis. And an hypothesis is a proposed explanation made based on limited evidence as a starting point for further investigation. So, and as you probably understand by now, this further investigation is where we're headed. This is where we want to go. So we do this by asking what ifs. What if the database goes down? What if we have a latency in Redis? What if we have an AC failure? And it's easy to focus on the infrastructure part here, but remember that this chaos, this failure, is something we can inject in any layer of the stack. So what if we introduce a bug into our code? What if Slack is down? That's a major issue for most. What if Mike isn't at the office today? And we're building our hypothesis with the scientific if-then method. So if this happens, then that. And if your hypothesis ends up being, if we do this, then things will break, well, then there's no need to run that experiment because we know things will break already. So instead, go back, fix it, start over, create a new hypothesis. Now we have our hypothesis. So now we're ready to start planning our experiment and then running it. And when we are planning and designing the experiment, we try to involve everyone that actually is involved in that part of the system. So we gather the right people in a room, and we whiteboard the experiment usually. So we look at the architecture, look at how we're going to do the actual experiment, and what we think will happen when doing it. And by gathering these people in the room, we usually learn a lot every time we create a new experiment. People who might not usually talk to each other will do that in this forum. And when we create our experiment, we need to think about containing what's called a blast radius. And the blast radius is how big the impact should be able to be in our experiment. And this can be set to a certain service. It can be set to a single AC. It can be set to 10% of users or to the country Norway. We contain the blast radius to make sure that we don't affect the entire system. And we should always start as small as possible and then grow the experiment as we gain confidence. Chaos engineering is a team effort, so make sure to involve everyone in this. Let people know what you're doing and why you're doing it. You don't want to surprise people with incidents. Even if you're in the test environment, having an incident in a test environment might affect developers trying to develop. So make sure to notify people. And this is also another way of building confidence and trust in the organization. And lastly, but very important, is to make sure to have a way to abort your experiment. Have this big red stop button. And you don't want to have an experiment that runs out of control. You need to be able to stop it when needed. And someone said that you want to scrape skin but not draw blood, and I think that's a fine way of putting it. So now we've created our experiments, we've run it, and now it's time to look at the results from the experiment. Remember earlier I talked about the steady state? Those metrics that we defined then, they are the ones we're going to use now to prove or disprove our hypothesis. And when we created the hypothesis, we had limited evidence. But now, doing the experiment, having done it, we should probably have a lot of evidence to tell us if it was proven or disproven. So we, in a very controlled way, injected failure into our system. And the question now is, was the system robust enough or adjustable enough to handle that failure? When we created our hypothesis, we expect things to happen. But since it's made based on limited evidence, we don't really know exactly what will happen. That's the thing with complex systems. So the inherent chaos that is in every system might give us some unexpected results. It usually does. And that's not always negative either. We might find what's called mitigating factors as well. That is, things that made the incident smaller than we perhaps thought that our system would make it. And once again, we want to involve everyone. So when we have done our experiments and we have results, we want to share the progress, make sure everyone knows what happened. We want to share our success. And the question then is, what is success when it comes to chaos engineering? And I would say that if you have been able to run an experiment, that is success. If the system was resilient to the failure, that is success. Did something break? Well, that's also success, because then you've learned something new about your system. You're able to improve on your system to not have that incident in the future. So if any one of you has ever been involved in a post-incident review, this is kind of what we're doing here. So we're having this post-incident review, but this is the incident that never happened. Instead, we're doing this in a very controlled way, so we're able to learn about our system. So what happens now? Well, we have action items, we have bug reports, and so on, just like we do with any incident. So this is where we actually learn from incidents. It's just that this is the incident, like I said, that never happened. So we use these learnings to improve on our system. We fix those issues. With the confidence we gain when we've done our experiment on a certain scale, we're now able to expand, increase the scope. So if we used 10% of users, now we can increase to 20% perhaps, and see what happens then. We can include more hosts, a bigger part of the system, other countries. And when we increase the scope, we usually find new things. We see effects that we don't really see on a smaller scale. Adding latency to 20% of HTTP calls instead of 10% will probably give you quite different results. So, now we know how to run chaos experiments and what chaos engineering is. And it's actually quite straightforward. So that brings us to the serverless part. And if any one of you is now thinking that, are there challenges with serverless? I think that's good, because then you'll hopefully learn something new today. This is the AWS definition of serverless. Serverless allows you to build and run applications and services without thinking about servers. And that's awesome. This part, without thinking about servers, that always makes me happy. I don't like to think about servers. And you probably all heard the old, there are still servers in serverless thing. And there are, it's just that we don't manage them. And that leads us to some of the challenges. Since we don't have any servers to manage, we have instead potential sources of failure that we don't or can't control. The failure modes for serverless is quite unknown to us. And I'm all for less infrastructure work. Yay for less heavy lifting. But every time someone sets up infrastructure, every time someone provisions infrastructure, they usually learn a lot about the failure modes. They learn how to configure it. They also often learn how to fix issues with it. We don't know that much about the underlying stuff with serverless. So things are unknown for us. Besides Lambda functions as the most common part of our applications, we have so many services to choose from. Every one of those have their own failure modes, their own sources of failure that we don't know about. We have DynamoDB, we have SQS, SNS, EventBridge, AI, ML services, and whatnot. For each function and for each service we use, we have configuration and security policy settings per function and per service. And that's great for control, but that also means that we risk of having configuration issues and security policy issues for each function and each service. And when we build our serverless applications, we usually have more granular architectures. That means that we have more of everything. We have lots and lots of functions, and we have lots and lots of services, and each have interconnections in between those. So all in all, we have more inherent chaos in serverless applications. This is a great quote. Chaos engineering is a perfect fit for serverless. If you can't get anyone else to say it, you just have to quote yourself. But what I mean by this is that serverless, with its inherent chaos and the granular architectures, is well suited for doing chaos engineering. Using chaos experiments, we're able to build more reliable and resilient applications with serverless. And to be honest, we don't really need that much more than the AWS CLI to get started. So, speaking of quotes, don't quote me on this, but doing chaos experiments on legacy is quite easy. It's easy to get started. Shutting down EC2s, destroying pods, crippling network traffic. But we have control of the underlying infrastructure in most parts. But with serverless, since we don't, it's a bit trickier. But it allows us to be creative as well. And most of us building serverless applications, well, we probably do more advanced stuff all day anyway. So it's really no issue to get started. So let's start by looking at some common serverless weaknesses. are we handling errors correctly in our applications? When there is an error inside our application, how do we handle those? No matter if it's inside our code or if it's in one of the services, we better make sure that we know how our application handle error. And releases like dead letter queues for SNS, that's really great that AWS releases those types of features, because it means that we don't have to handle errors in our code anymore for that specific purpose. And enabling it, easy, but make sure to test it as well. Seeing that one SNS message isn't delivered, well, that's one thing, but what about 1 in 100,000 or 50,000 out of 100,000? What happens then? How does your application handle that? With Lambda functions and dependencies on other services and third parties, we better make sure that our timeout values are correct. And in most cases, I think they probably are when we're talking about the steady state. But what happens if there are issues? Say you have latency in your applications. Are your timeout values still correct? And with event-driven architectures being more and more common, the event is key for our application. So how do we handle those events? How do we queue them? Are we queuing them correctly? What happens to events in case of service failures? And using many services and third-party dependencies means that we trust them to be there. What happens when they are not there? Do we have fallbacks in place for DynamoDB or whatever third-party service we're using? And I don't want to jinx us, but regional outages rarely happens. And having regional failover or multi-region in our serverless application isn't just for regional outages. There might be other things as well. A major ISP might have issues causing latency for your users reaching a certain region. Do you have regional failover? So let's look at some practical serverless chaos experiments we can do. Our simple architecture here is a web service with an API gateway in front of 2 Lambdas. And they, in turn, retrieves or stores data in DynamoDB. Alongside this, we have an S3 bucket for static content. So in this, we can, for example, inject errors into the code. So instead of returning a 200 response through API gateway, we can return a 404 or a 502 or whatever error code we think is one to test with to see how does our application handle that. We can remove downstream services, testing fallbacks, for example. So let's remove DynamoDB, restricting access to DynamoDB. What happens to our applications in those cases? We can alter the concurrency of functions. And this can be either to simulate issues with traffic to our functions, or it can be to simulate a provider issue if ever AWS has issues with Lambda. And we can restrict the capacity of tables, once again, to simulate issues with DynamoDB's service. But we can also do quite simple things by security policy errors. A lot of issues that we see, incidents that happen, outages, are caused by issues with configuration or with security. We can add the coarse configuration errors into our application, restricting or limiting how access to API gateway is allowed. We can add service configuration errors, of course, to any type of service that we're using. Or if we're using Lambda disk space, if you're using the temp directory in Lambda, what happens when that fills? If your temp directory gets full? Well, we can do an experiment and fill the temp to see how our application handles that. Or This is the mother of serverless chaos experiments, latency in the functions. Serverless hero Yang Kui wrote a great article on this, I think about 2 years ago. He's the OG when it comes to serverless chaos engineering. AWS evangelist Adrian Hornsby added on this by creating both a Lambda layer and Python libraries to be able to test latency. And by adding latency, we're able to simulate different things. For example, cold starts. Cold starts perhaps is a smaller and smaller issue today, but let's make sure that we know how our application handles latency. We can simulate cloud provider issues, like if there is issues with Lambda, adding latency. Or we can simulate runtime or code issues. If we have issues with the code that we have created, it might add latency. Well, we can test that to see how our application handles it. Integration issues is quite a common one. Let's say that we test what happens when we're using a third-party dependency, and that has latency. If we have a service to send text messages, for example, what if there is latency added to that call each time? How does our application handle that? And of course, to test our timeouts. Like I mentioned earlier, we can add latency to our Lambda functions to see what happens when we have timeouts for our Lambda functions. So, enough theory, I think. Let's do some chaos in a serverless environment. To help people get started with doing chaos engineering for serverless, I've created a simple web page called the Serverless Chaos Demo Site. It's simply to show how easy it is to get started doing experiments on a quite small serverless application in this case. And this one uses Adrian Hornsby's failure injection layer to do the actual experiments. And the architecture is, as you can see, pretty much the same as the one we looked at before. We now have 3 Lambda functions instead. So static content in S3, we have an API gateway and 3 Lambda functions. And these, in turn, are then calling DynamoDB to fetch, in this case, URLs for new images to load on that web page. So it's simple and straightforward. And each of these Lambda functions are then equipped with the failure injection layer so that we are able to inject failure into them. So, do you remember the steps we had when we were creating our experiment? Let's say that we have established a steady state already. Now it's time to create our hypothesis. So what if my function takes an extra 300 milliseconds for each invocation? What if my function returns an error code? What if there is an exception in the code? Well, in that case, my hypothesis, based on the limited evidence I have, is that if we inject failure to functions, then my application will use graceful degradation. And graceful degradation means that the application will still work good enough for the users. So, let's switch over. Cool, so this is the site. Timeout. Now it should start reloading images. Timeout. That's good. And it's loading. Okay, so looking at how this works. So we have it's a serverless application using the serverless framework. and it has the 3 functions, and on each function we have the Lambda layer added. The Lambda layer in turn has some parameters which we store in parameter store. So these are the 3 functions. Loading. There we go. And for each function, we're storing parameters regarding the failure injection in parameter store. Here we go. So simple value in this case, if it's enabled or not. If it's latency, then how much of a delay we're adding. We have, if we're using the error code injection, which error code to inject. Or if we're using exception, what exception message to create. So, and since this is stored in parameter store in this case, we're able to update it quite easily, either by using the AWS console or by using the CLI. So let me just get one of those. So this is the command. We're using AWS SSM put parameter. And then we have the string, which is the one that is stored in parameter store. Just change it to true. There we go. So easy to just add this parameter. And you remember I talked about the stop button, that we needed that. And the stop button in this case, well, it's just about changing back the parameter from true to false instead. So let's switch over again. Let's see. One is loading. And then we're getting a failure. Cool. So, loading. Loading. So function 1 now has, as you can see here, it's loading and it takes about 472 milliseconds, or exactly, which means that we've added latency in this case to it. Normally it should take about 200 milliseconds or just below, which these other 2 do. So let's update one of the others. The second one is for the error code. In this case, we'll inject, instead of getting a 200 response as we normally do when our function runs, we'll instead add a 404, which means that it should then fail. Sorry, I need to change it to enabled as well. True. It's quick. So that's function number 2. And now, instead of getting a 200 success, for this function, we're getting a 404 error. And in this case, the graceful degradation is that it's showing a failure image instead of showing one of the regular images that it should normally do. So we're having the possibility to add both latency. We've added the 404 error. And now let's change the last one and add an exception message. True. Copy and paste. Cool. There we go. And when it reloads, there we go. Now we're getting it says status 0 error, which means that an exception has been created in this function. And in this case, the function handles it by, or the application handles it by showing a failure image once again. So we have graceful degradation in place for both timeouts, for 404s, and for exception in this case. And so that's an easy way of doing chaos experiments by using the Lambda layer that Adrian Hornsby has created, or using his, I think he'll rather have you using the Python library instead. So you can just pip install it into your Python application. And by doing these experiments, we're then able to test to see how does our application handle these types of failures. So if you want to try this out, just go to this site. You'll have the URLs as well to be able to try it in your applications. There we go. And that brings us to the summary of the Performing Chaos Engineering in a Serverless World session. And we've established that everything fails all the time. And I think by having this mindset, we're able to build and operate systems more reliably. And it will help us to create more happy users. And remember that using serverless functions and managed services, it gives us a toolbox to build robust applications. But serverless in itself doesn't make your application resilient. It's still up to the architects, to the engineers, to the developers to build a reliable, robust, and adjustable application. And we create our chaos engineering experiments to draw out weaknesses and to fix them before they actually cause an outage. And by doing controlled experiments, we're able to build confidence in our system and how the system works. But as important is that we build confidence in our organization. And remember the human factor and how good it feels to sleep at night. And by now, you've hopefully seen that using chaos engineering is beneficial, and that it's not that hard to get started with. It's easy to find excuses not to do chaos engineering, but I think you now have a lot of reasons to actually do it as well, to help build more reliable and resilient applications. If you want more, of course, follow me on Twitter, but also follow Serverless Chaos, which is a bot which retweets information about chaos engineering. You can try the Serverless Chaos demo app, as I said. On my website, I have some links to YouTube videos and repositories around chaos engineering. You can join the Chaos Engineering Slack as well to engage with the community and learn more from others doing chaos or wanting to do chaos. And look for local meetups around chaos engineering. There are all over the world today. And we are actually having a meetup here at reInvent tomorrow at 8 p.m. So if you want to join that, please just reach out to me. Cool. Thank you very much.